Hello, and welcome back to Introduction to Genetics and Evolution. In the previous videos, we've been trying to distinguish what fraction of phenotypic variance, how much of the variation you see in traits like height, skin color, etc., come from genetics versus the environment. In this video, I'll introduce you to what's referred to as the breeder's equation. But first, let me recap a couple of points. Now, the trait variance we're interested in, so this is any trait you could be looking at, such as height, eye color, anything that you can quantify in some way, has some genetic fraction and some environmental fraction. And we can symbolize this with a very simple formula. Vp, which is the phenotypic variance, is equal to Vg, that's the fraction of the phenotypic variance that is genetic, plus Ve, which is the fraction of the phenotypic variance that comes from the environment. Now again, we want to quantify how much is genetic versus environmental. The concept I introduced last time was that of heritability. That is the proportion of the total phenotypic variance that is genetic. Now this is important because this genetic component is the component that can respond to selection, whether that selection is natural or artificial. Now again, since this is a proportion, it ranges from 0, meaning that all the variation is environmental, to 1, meaning all the variation you see is genetic in origin. Now, we talked about means of identifying this before, but a new means I want us to start looking at here is in response to selection. Now, this picture shows several students. The ones in white are girls, the ones in black are boys. The average height of this population, as you can see, is about 5 foot 7 inches. Now, let's imagine that we take the circled individuals here, that guy and that girl, and let's say they had a bunch of kids. What would we expect? How tall would those kids be? Now, one possibility is they would be, on average, about 6'0", just like their parents. That's a possibility. The other possibility is they might be 5'7" on average, just like the overall population. Now, these are two very different outcomes. Now, if height was purely determined by the environment, then we might expect this latter one. We might expect that the offspring would look like the original population, because it didn't really matter who the parents were. In contrast, if height was purely genetic, then we might expect the kids to look just like their parents because they inherit the genes from their parents. Well, we can calculate heritability by looking at this response to artificial selection, by looking at individuals who are not representative of the original population, breeding them and seeing, what happens in terms of their offspring. So let's use corn, one of my favorite examples, and let's say you're looking at corn height. And let's say corn height averages around 5 feet. Okay, so in the population you're looking at, that's the average height of ears of corn, or of plants of corn. Let's say you select a group of 7-foot tall corn and you breed them. Now, if the offspring of these 7-foot tall plants averaged 7 feet also, so you looked at a lot of individual offspring, on average they ended up having a distribution that looks something like this, right? Then that suggests that the variance that we see here is purely genetic. The heritability is 1, because you see the offspring inherit the traits of their parents completely. Okay. In contrast, if the height of the 7-foot plants were actually 5 feet instead, so instead the offspring looked more like this, then that suggests the variance in height is purely environmental, or heritability of 0. So this was a heritability of 0. I showed you previously the heritability of 1. What would happen if the height of the offspring of the 7-foot plants would average 6 feet? What might you expect heritability to be? Well, it's a very simple answer. Well, 5 feet meant it was 0, 7 feet meant it was 1, so 6 foot would unsurprisingly mean the heritability is 0.5. Right? Well, we can do the same thing and divide this up. That, again, if they average 5 feet, the heritability was 0. If they average 6 feet, it's 0.5. In between, if they're 5.5 feet, it would be 0.25. Essentially, what we're looking at is we're looking at the point from where we started, which was 5 feet. That was the starting population average. We're looking at the average of the selected group, which in this case was 7, and we're looking and seeing the offspring. How far did they get from the starting population average to the selected population average? The fraction of the way they make it is the heritability. And that is true, and that is actually how you can estimate the genetic component to whatever trait you're looking at. Now let me give you an analogy that might make this a little bit easier to see. This is a map of a subsection of the state of North Carolina where I live. So I live over here in Durham, North Carolina. That's where Duke University is. And let's say I was trying to go from Durham, North Carolina, along this interstate. This is I-85, I think. I can't remember. Let's say I was trying to go down to Charlotte, North Carolina. Now, if you start in Durham, you're trying to get to Charlotte. This is 150 miles away. That is similar to the selected group. So the starting thing was here. The place you were trying to get was over here. But let's say I only got to the city of Greensboro. I only got 50 miles from here. So what fraction of the way did I make it to my destination? Well, I was trying to go 150 miles. I only made it 50 miles. So I made it a third of the way there. Well, that's the same concept when you look at artificial selection and estimating heritability from it. That you're starting with a population average of 5. You're trying to get to this average, because this is the selected group. So these are the 7-foot tall corn. So the distance I was trying to go here was from 5 to 7. So I was trying to go 2. And in fact, I only got 1. Right? This is the new populations, or the next generation's average, which was 6. So I started with 5, was trying to get to 7, but I only made it as far as 6. So therefore, the heritability in this case would be 1 over 2. It's 1, which is the response to selection, over 2, which was the selected group. So in this sense, we can redefine heritability from one generation selection experiment. Heritability can be defined as how far you got, or the response to selection after one generation, relative to how far you were trying to get, or basically how intensely you were selecting. So heritability can be defined as R over S. The reason we can do this is because R is dictated by the genetic variance, whereas S is a combination of genetic and environmental variance, because that's what was in the original population there, right? Because again, as I mentioned earlier, the response to selection can only be through genetic variance. Now, again, this measures the fraction of phenotypic variation that is genetic, because this is equivalent to Vg over Vg plus Ve, or, as we said before, Vg over Vp. So let me give you a sample problem to try. Let's say you're selecting for plumper turkeys to have, a nice dinner. Let's say you start with a population of turkeys that average weight 25 pounds. Let's say you select turkeys with an average weight of 45 pounds from this overall population, right? So in the population, let's draw how this might look. Here's the distribution of weights of turkey. Here's your 25-pound turkey. There are a subset that are 45 pounds. So you select this group. And let's say the offspring of these 45-pound turkeys weigh 40 pounds. So the offspring may be like here. What is the heritability of weight in these turkeys? Try this problem. Welcome back. I hope that wasn't a very difficult problem. Again, we're starting with 25-pound turkeys. We're selecting for 45-pound turkeys. And the offspring that we got were 40-pound turkeys. So what is first the intensity of selection here? Well, we're trying to go from 25 to 45. So in this case, S equals 20, because that's the difference between 45 and 25. The response, in this case, we started at 25 and we only got to 40. In this case, that is 15, which comes from 40 minus 25. So R over S would be equal to 15 over 20, which in this case would be 0.75. So the heritability in this case is fairly high. That 75% of that variance that we see is genetic in origin. Now, I should remind you, these are not perfect predictions, right? Now, this is just giving you an estimate of heritability, and this comes back to the points I raised at the very end of the last video. The amount of environmental variance is not necessarily constant. Some populations may have more or less genetic variance than other populations. This is what you saw for your turkeys in your farm. In another farm, you may get a different outcome. And you have to remember what you're calculating. You're looking at the fraction of total phenotypic variance in the population you're studying that is genetic. So that is the Vg over Vg plus Ve. But again, this is very important, and this is something that's not only utilized just in the context of artificial selection, but this is important for both artificial and natural selection. With artificial selection, these are very, very similar concepts. The breeder is choosing desirable traits and has organisms with the most extreme desirable traits breed to do them. So let's say, for example, you're trying to select for friendlier collies. You take your 2 friendliest collies and you breed them. The same sort of thing happens with natural selection. That particular traits will facilitate survival or reproduction, and organisms with the most extreme such traits end up having the most offspring. So the same principle applies. And again, the response to either kind of selection, whether it's natural or artificial, is always going to be in terms of the genetic variance. Well, thank you very much. I hope that was helpful. Hello. and welcome back to Introduction to Genetics and Evolution. In the previous videos, we've been looking at concepts related to the amount of genetic variation in populations relative to the amount of total phenotypic variation. Now, as I mentioned before, this genetic variation is that subset of the variation which can be used by natural selection. So let's talk about natural selection for a minute and apply this to a couple of other areas. And very soon you'll see we'll be transitioning into population genetics. Well, natural selection is both non-controversial and, as I mentioned before, it is a mathematical inevitability. It's a mathematical inevitability if three simple conditions are met. First, you have phenotypic variation. We talked about phenotypic variation just recently in the context of quantitative genetics, and that would be that VP is not zero, that basically everybody doesn't look exactly the same in every way. Some of that phenotypic variation you see is actually inherited or genetic. In that regard, we're saying that the heritability is not zero. So you see, I'm introducing the same terms we did before, but now with some quantitative genetics behind them. And last but not least, this variation that is inherited, must affect either survival or reproduction. Now, let's walk through this very simple cartoon which illustrates this point nicely. So here we have several peppers that vary in their mildness or hotness. There's some that are mild, some that are hot. So there is this variation. This variation is inherited. The mild peppers give birth to other mild peppers. The hot ones breed other hot ones. Here's an interesting point I haven't emphasized so far, but this is relevant for today's lecture. More individuals are born than will survive to reproduce. Now, our capacity for population growth tends to be very high. We'll come back to this in just a moment. And related to this, some variants that survive or reproduce at higher rates than others. In this case, we can see that the milder peppers don't survive as well as the hot peppers because the mild ones get eaten up by things like mice or humans who like mild peppers. The outcome of this is that the population changes over time. That over time, as this is iterated over and over again, more of the surviving peppers will be hot because you've eliminated then not only the mild peppers themselves, but even that genetic contribution within the population that made the peppers mild. Now, if we go back in time, that original concept of natural selection was very intrinsically tied to that of population growth. And Darwin's ideas were very much influenced by Malthus, who was an economist. Malthus had pointed out that populations are actually kept from growing by limited food and resources. Because again, our capacity to breed is very, very great. And if you provide more and more food to particular species, you'll tend to see that they will reproduce at a higher rate than is needed just to recreate the number of individuals present. That basically the population will grow if it is able to grow, almost always. Now, Darwin pointed out that this limitation produces struggle wherein some subset that are better able to survive or reproduce will tend to spread. But let's look at this concept of population growth. And why is it that natural populations grow so much? Why do we see this potential for great growth? Well, the capacity for growth is huge in most species out there. Now imagine, to maintain a constant population, assuming population was sexual, assuming you need a pair of organisms to breed, each pair would only need to produce 2 surviving offspring. Now, if conditions are favorable, how many offspring can most individuals produce? Well, look at some plants, for example. Let's say you're looking at seeds or pollen. Here's a picture of a tulip stamen and all the pollen on it. Look at all those individual grains of pollen on there. How many possible offspring could that tulip have? Definitely a lot more than 2. Think about insect larvae. You know, if you let an insect breed, how many offspring can it have? Think about things like cane toad eggs. Cane toads, as I mentioned a long time ago, are an invasive species in Australia and also in Hawaii, and they can have, hundreds, thousands, of offspring just from one breeding pair. And it's even true for humans, that if humans were allowed to in some way, we could potentially, one couple could produce many, many, many kids, easily, 10, 20, something like that. Now, we like to model the rate of increase and see how it's actually happening. Well, populations can be modeled with what's referred to as a stable rate of increase. This is assuming that a steady fraction of the population, or the population increases by a steady proportion year after year. To model this, we need a couple of parameters. We need a birth rate, which can be modeled as, for example, a number of births per 1,000 per year. We need a death rate, number of deaths per 1,000 individuals per year. And from this, we can come up with what's referred to as the intrinsic rate of increase of a population. That is very simply the birth rate, so the input, minus the death rate, which is basically the output from the population. So in the United States, as an example, the birth rate is about 14 per thousand. The death rate is about 6 per thousand. So that makes the intrinsic rate of increase about 0.008. In this case, this is not considering immigration. This is just looking naturally. What this means is the population will grow naturally by 0.8% per year. Now, if the birth rate is greater than the death rate, then the population grows. And conversely, if the birth rate is lower than the death rate, then the population will decline. Now, so let's look at the effect on population size. Now, we'll go through a little bit of math here just to work this out. I hope you don't mind. So let's say that n is the population size and t is time in years. Now, we can identify a standard rate of population growth as dn over dt, or change in population size over change in time. And that would be equal to that rate of increase times the population size. Now, if we want to get an algebraic solution, if we assume that this was a constant process, we can approximate this as n sub t, so the population size at time t, is equal to n sub 0, which is that starting population size, times e. E is the algebraic number you often see. I think it's approximately 2.71. E to the power rt, r being that intrinsic rate of increase, and t being time. So time may be measured in years. So what is the population doubling time? How long does it take for a population to double its number of individuals, right? Obviously, that's going to be related to r. It's going to be related to the rate of increase, that if r is very large, the doubling time will be very short. If r is very, very small, then the doubling time will be very long. But let's put some actual numbers on this just so you can see. So this is the formula I showed you before. N sub t equals n sub 0 e to the rt. And importantly for this, n sub t is the population size at time t, at the end of the period that you're studying. What we want to solve for is we want to solve for the doubling time. The time it takes to go from a particular population size, let's call it n sub 0 at the beginning, to double that size. So we're waiting for it to go from n sub 0 to 2n sub 0. So what we can do is we can basically solve this formula by putting 2n sub 0 here into n sub t. Okay, and then what we're going to do is we're going to solve for t. The idea here is to look at basically how many generations it takes to go from n number of individuals to 2n number of individuals. So let's walk through. So we start off, as I said, with substituting to this formula. For n sub t, we put 2n sub 0, and we have 2n sub 0 equals n sub 0 e to the rt. Simple algebra, we just divide both sides by n sub 0, so we have 2 equals e to the rt. Now, how do we solve for t with this? Because that's ultimately what we're going for. What we have to do here is use the natural log. Remember, e is approximately equal to 2.71. This is a factor that's used quite a bit. You have a button on your calculator that probably says e to the x, and another button that says ln. ln is the natural log. So what we do is we take the natural log of both sides. Take the natural log of both sides. So we said natural log of 2 is equal to the natural log of e to the rt. By the way, if you don't have a calculator that does this, you can just go into Google and type in ln space 2, and it'll actually solve that for you. So we take the natural log of 2, and that calculates out to 0.693. The natural log of e to any power is that power. So in this case, the natural log of e to the rt is rt. So we have now very simply 0.693 equals rt. Now again, we're solving for t. So what do? We divide both sides by r, and there we go. The doubling time is now t, which is 0.693 divided by r. So let's put some numbers into this. Well, we have a U.S. population at the time this was recorded of about 310 million. I mentioned before the population growth factor was about 0.008. So all we have to do is put in this r into the formula right there. So 0.693 divided by 0.008, and we have 86.6 years. Now think about that. That's just a little bit longer than an average lifetime. A lot of people live that long, and that's how long it would take until the population of the United States goes from 310 million to 620 million people. That is a lot of people, and that's fairly quick. This is assuming this sort of growth as we drew it here, but it's not unrealistic. Now, let me get you to try one, but I want you to notice ahead of time that you don't actually need to know the population size to get the doubling time. You basically don't need to know this n sub 0 factor. All you need to know is r. Solomon Islands. Here are some numbers I got from Wikipedia. The birth rate on Solomon Islands is about 35 per thousand. Death rate's about 5 per thousand. Population size today is 500,000, though you don't need to know that. How long would it take to get to a million? How many years would it take to get to a million? Well, I'll let you solve that problem here on the question online. Well, I hope that one wasn't too challenging. Very, very simple problem. What we want to do is we want to calculate R. R, as I mentioned before, is equal to the birth rate minus the death rate. So it'd be 35 per thousand minus 5 per thousand, which in this case would come out to 0.03. So that's your R. So when we want to calculate the doubling time, say doubling time, in this case T would equal to R, or 0.693 divided by R, 0.03, which in this case comes out to 23 years. That's really dramatically fast, isn't it? That's changing the population on these islands from 500,000 to a million. So you're doubling the population size in 23 years. Well, we've seen a lot of population growth throughout the world, and I'll show you some pictures from a recent article in Science. This first figure shows historic and projected future population growth. So you notice that the world population was very low, and we start seeing here very, very recently, just in the last couple of hundred years, this dramatic increase in numbers of individuals. So we hit 1 billion in the year 1800, we hit 3 billion in 1960, 4 billion in 1974, 5 billion in 1987, 6 billion in 1999, 7 billion in 2011, and it's projected we'll hit 8 billion by around 2024. This divides it up by some countries, where you're looking at some of the developed countries, some less developed countries, Africa as a continent, China by itself, and India by itself. So this is projections up to 2050 in this case for world population growth. Now, interestingly, our rate of population growth has actually gone down. Now, we are still increasing. R is still positive, that the birth rate is still exceeding the death rate, but the amount with which it's exceeding it has actually gone down over the last couple of years. But it's still positive, and that's why we're continuing to see this very rapid increase. Now, this is something that several different countries have attempted to address. One example would be China. China, as many of you know, back in 1979 instituted the one-child policy. This shows you the population growth in China over time. And this shows you the age distribution as of 2009 within. Now you may be thinking, like, well, why is this still going, right? Because we have the one-child policy instituted around 1979, 1980, yet we still see this increase. Interesting, if you look at this, the increase is actually closer to linear than it is to exponential. Like, it's not going up, it's not continuing to accelerate as you would expect. So this probably has actually had some effect on slowing population growth. But, again, the birth rate is continuing to exceed the death rate. So we're still seeing an increase in the population size in China, as in many other places in the world. Well, why is that? Well, again, we have two causes of population growth. There's high birth rate, and there's low death rate. So we can cut the birth rate, but we still see growth. And what that means is that the death rate is decreasing faster than the birth rate is decreasing. Now, that's not intrinsically a bad thing. Obviously, we like decreasing our death rate. We don't want to have people just die willy-nilly, of course. But this is a problem in terms of how many people are on the planet. Over the course of many countries and over the course of a lot of recent time, we've seen this declining mortality or declining death rate. And some of it is associated with things like the introduction of the use of soap, improved sanitation. Definitely things like antibiotics and other modern medicine have really increased life expectancies. I can show you how much too. This is just showing the difference between 1950 and 2010. And look at this. In Latin America and the Caribbean, we have an increase in life expectancy from 51 years to 73 years. In Africa, from 38 to 55. North America, 68 to 78. And just over the course of the whole world there, we can now expect to live 20 years longer than we could before. And as a result of this, we're seeing this just increased life expectancy at birth. And this, again, divides it up by several countries. Now, again, intrinsically, it's not a bad thing that populations grow. However, there is some maximum number of individuals that can be sustained on the planet. We'll come back to this question in the next video. Thank you. Hello, and welcome back to Introduction to Genetics and Evolution. In the previous video, we talked extensively about population growth rate. I identified for you the intrinsic rate of population increase. and that is the birth rate minus the death rate. For most species, the birth rate tends to be much higher than the death rate, meaning the capacity for growing is very high. In this video, I'd like to introduce to you the concept of carrying capacity. That is the maximum number of individuals that can be supported in an environment the way it is. I showed you this slide previously. This is looking at human population growth over the last several thousand years and projecting into the future. And you can see human population growth is very high. Our birth rate greatly exceeds our death rate presently, and you can see this by this increase in number of individuals over time. Now, our growth rate has slowed since the 1960s, 1970s, so meaning that the difference between the birth rate and the death rate has gone down, but it's still positive. There still are more people born than are dying. Now, intrinsically, this is not a problem, but what if there are not enough resources to sustain everybody? Well, this again ties into that concept of carrying capacity, which is often abbreviated as K. Now, this is the total number of individuals that can be supported within a population. Well, what determines this carrying capacity? What determines how many people can be supported in a population? Well, the answer is it's determined by the environment. Now, the question is, what happens when you exceed this carrying capacity? What happens when you go too high? Well, there's two things that can happen. The number of individuals that are present cannot be supported. So either you have to have a very sudden decrease in birth rate that everybody holds back reproduction. That typically doesn't happen in most species. Or you can have, unfortunately, an increase in the death rate. So let's think about the impact of human population growth. Now, our world population already exceeds 7 billion people. Now, most of this growth, as I mentioned, has come about and is sustainable so far because of increases in hygiene, in medicine, etc. So, and also additionally to that, we are much better at producing food, and etc. And technology has compensated and has prevented these mass famines. There are still some famines in some parts of the world, but technology has definitely helped. But the question is, how long will this last? For many years, people have talked about a population bomb, that at some point in time we're going to hit the wall. Now, again, technology has staved this off for part of the world, but not all of the world. What's going to happen next? Well, let me ask a different question first. Why haven't we all starved yet? Why is it we were able to get all the way above 7 billion? Well, again, so far, food production, and this is averaging across the whole world, again, some parts of the world don't have this, food production has increased faster than population increases. That food production has actually increased threefold, while population has only increased twofold in the span of this figure here. Now, that can only work to a certain degree because the food that we're using can only be produced so fast, and we're continuing to reproduce at very high levels. So let me give you a problem to try. Let's use the formula I gave you before. N sub t, which is the population size at time t, is equal to n sub 0 e to the rt. Let's say the current world population is 7 billion. Let's pretend I just made this number up. The carrying capacity of the Earth is 20 billion, and let's say that's a future carrying capacity. And let's say that R is 0.012. That's the difference between the birth rate and the death rate. How many years until we have massive deaths? Well, I think that was a pretty straightforward problem. Again, we have the formula, n sub t equals n sub 0 e to the rt. Now, what we're looking for is this getting to this carrying capacity, and we'll say that's the time we're looking for. So n sub t then would be 20 billion. That's the carrying capacity we identified. N sub 0 is 7 billion. That's approximate for the current population size. Not exact anymore, but it's close. And R is equal to 0.012. Well, we put in all the numbers just as we had before. 20 billion equals 7 billion e to 0.012 t. So let's solve this out then. We divide 20 billion by 7 billion, and we get from that 2.85 is equal to e to the 0.012 t. Okay, so all I did was divided 20 billion by 7 billion. That's how I got this. So I take the natural log of both sides. The natural log of 2.85 is just a little bit over 1, so that would be 1.05 is equal to 0.012 t. Okay, now I divide both sides by 0.012, and what I get is t is equal to about 87. So 87 years. Now, I assume the world can hold 20 billion people. That may or may not be true. That may be a high estimate. Maybe that's more than can actually be supported on the Earth. It could be a low estimate. But 87 years until we start seeing massive deaths. Well, is it going to be massive deaths? Well, what happens when we hit the carrying capacity? Well, one possibility is we may see a sudden crash. So this is a typical graph you'd see where you exceed the carrying capacity and then boom, the population goes down. And it goes down dramatically. So what caused this would be a lot of people dying. This has been observed in some cases. This shows, as it depicts over here, the population of the St. Matthews Island reindeer herd. We saw this dramatic increase in numbers and then a very sudden loss of resources and boom, crash down. That was very unfortunate. You may also see a leveling off. You may see it goes up and then it comes down a little bit and it oscillates, stays around the carrying capacity. This was observed in some classic studies using paramecium, where here's P. caudatum or P. aurelia, that it would increase to a level and then it would level off. Now, leveling off sounds good, leveling off at a carrying capacity, but you have to think of what does this actually mean? When you level off, you're either having a decrease in birth rate. I'm not sure if you're actually going to have that. The alternative is you're having an increase in death rate. That is obviously less positive. Now, you may see different outcomes in different places. Maybe in some parts of the world you would actually have a decrease in birth rate enough to level it off. Other parts you may see an increase in death rate. But this leveling off, or what's often referred to as the logistic model of population growth, is not necessarily a very good thing to happen. I mean, it's good in the sense it stops population growth, but it's bad in that it often means we're having an increase in our death rate. So if things are remaining unchanged at some point in time, human population growth will exceed our ability to support that growth. So what do we do about this, or what do we do next? Well, there have been some proposals of what to do, and I mentioned the one-child policy, which was an attempt to decrease the birth rate. There have been more disturbing ones, though, too. So Ronald Fisher, who is the person who actually invented the analysis of variance test, Ronald Fisher suggested in his 1930 book, and this is a very disturbing proposal, the most obvious requirement for a society capable of making evolutionary progress in accordance with its current needs is that reproduction should be somewhat more active among its more successful than among its less successful members. It's a direct quote from his book. So basically, he was advocating, as he put it himself, a moderate superiority of upper class fertility. That basically we should let people in the upper class reproduce more than people in the lower classes. That is a very disturbing proposal, one with which I don't agree at all. We'll come back to this thing, though, later in a later lecture, which is referred to as evolutionary applications and misapplications, with emphasis on that latter point. Now, you may be wondering, how accurate is this math? I mean, I just gave you a bunch of numbers there, and that looks a little scary, but is this actually meaningful? Well, there are some assumptions. One of the assumptions is assuming constancy. It's assuming that the intrinsic rate of increase doesn't change. And we know that's not always true. And we know, again, that the rate of increase is not the same in all different populations. When you look at the developing world, for example, the rate of increase is much faster than in the developed countries. And what this is showing you is an age pyramid. On the left side of each line here is the number of males. On the right side is number of females, and this is population in millions. And the y-axis here is age. So in this case, there's a lot of very young individuals, not so many old. In developed countries, we tend to see fairly even distribution of age. There's about as many 60 to 64-year-olds as there are 20 to 24-year-olds. And you can see this by the numbers, too, that in sub-Saharan Africa, 43% of the population is under age 15. In contrast, in Europe, only 16% of the population is under age 15. Same sort of difference when you look at the older ones. In Europe, 16% of the population is age 65 or older. In sub-Saharan Africa, it's only 3% of the population. So this is going to affect the rate at which populations are increasing. And the numbers I gave you are assuming this constant age structure, which you won't necessarily see. You'll often see this difference between rapid and slow growth. The other thing is that carrying capacity can change, right? So you can have innovations in farming. That would be a positive change, where maybe those innovations will allow more food to be produced than it was able to be produced before. That might raise the carrying capacity and stave off the problems. In contrast, you could have depletion of non-renewable or less renewable resources. That would be very negative. And that's probably what happened in the context of those island reindeer that you saw before. That there was some resource that they were consuming, and once it was consumed, it was gone. And it was gone not such that it could just come back the next year, but it was gone for quite some time. That could dramatically reduce the carrying capacity. And it could cause it to start at one place and then in future generations be much, much lower. So you'd have a much more severe crash than you would otherwise have. You could also have other changes in the environment that again, make it so you cannot support as many individuals. Some species, as we mentioned, exhibit these booms and busts, while others have more of a cyclical process. So again, this is the St. Matthews Island reindeer herd. Went up very high and then crashed very, very hard. In contrast, this is the case of the lynx and hare in Canada. And we see these population cycles that, rabbits become very abundant, lynxes eat them, lynxes become very abundant. After lynxes become very abundant, the rabbits are mostly gone. Lynxes crash. The rabbits then grow after lynxes crash. So you have this, booms and busts over and over again. Honestly, we don't know what's going to happen in the future. And, these are all just possibilities that we're looking at. The important thing here is we can mathematically show that this is something to be aware of and concerned about. And ultimately, the math isn't perfect, but it's a starting point, just as I said before in the context of heritability. And this is informative for particular circumstances or for generating. Thank you for your time. I hope this was interesting.